Hey, good morning, everyone. Welcome back. My name is Alex Bassini. I'm the Business Development Manager here at AWC Solutions, and we're joined by Scott. And every time I pronounce your name, and apparently every time I spell your name, I also get it wrong here, Scott. So I apologize for that. Today, we are going to go over something that's a little unique. UV advanced oxidation has been around for a while. I think tweaking it and understanding it is something that we're trying to cover today, which is I think is going to be great. We have done another one on UV. I want to say a good 3 or 4 months ago. So this kind of ties into that, and then there's some other things that are attached to this. So with that, if this is your first time here, welcome. We've done a whole whack of these already. There's a whole series of them. If you've missed any of them or you want to do a quick review, they are on our YouTube channel, and I'm going to be sharing a link in there so you can go in there and go through them all. So today we're going to be focusing on the advanced oxidation portion of it. Again, a quick background on AWC. We have been around now for 40 years. We have close to 600 water and wastewater treatment plants worldwide, working on a couple exciting ones right now that I could share. We're working on a pretty big job right now in Mexico. The whole bidding process is pretty fun, but that's us. We do divide everything because it's all modular in water, wastewater, and skid-mounted systems. So enough about AWC. We're going to go ahead and jump in to the UV advanced oxidation process. So Scott, if you want to go ahead and share your screen, it's all yours.
Thank you very much, Alex. Hopefully everyone can see my screen just fine. As you said, my name is Scott. So first of all, let me say thank you very much for the opportunity to talk to everyone about this technology. So for the next 10 minutes or so, we're going to be reviewing the UV advanced oxidation process, or UV AOP for short. And my first slide kind of just provides a quick overview as to what is incorporated into a UV AOP system. So to begin with, we have an oxidant, sort of the key catalyst. And for the purposes of this presentation, the main oxidant is going to be hydrogen peroxide, or H2O2. That is what is most commonly used in these systems, even though there are alternatives in certain situations, but I'm not going to dive into those details. If you have questions about that, feel free to bring them up in Q&A. Usually an oxidant is stored in a container, and you also have a dosing skid, some oxidant water of UV chambers, the bigger part of this particular image. And inside these UV chambers is where the so-called magic happens of chemical contaminants. And this happens through two sorts of processes that are happening instantaneously inside a UV chamber. First, you have direct UV photolysis, in which UV light interacts directly with a particular contaminant. That contaminant absorbs UV, and that results in the breakdown of its molecular structure. The second one is called UV oxidation, and this is where the hydrogen peroxide comes into play. So the H2O2 that was injected into the water is also photolyzed by UV light, and the H2O2 then becomes what are known as hydroxyl radicals. And these radicals are just that, very radical, very unpredictable in their nature. They bind to anything they can find and oxidize it, particularly contaminants of emerging concern. So you can see here a hydroxyl radical interacting with a contaminant. That interaction results in the oxidation of the chemical bonds and breakdown of the contaminant. So what's important to remember here is that we have UV photolysis and UV oxidation, and for most contaminants of concern that are hoping to be treated, usually it's a balance of both of those processes to result in a complete UV AOP system. So what is this technology used for these days? Primarily, the primary application right now is arguably groundwater remediation. And if you go online and you look at some of the work that's being done on Long Island in New York State, particularly in Nassau County, with respect to 1,4-dioxane, you'll learn a little bit more about this particular application. 1,4-dioxane is a groundwater contaminant that's very resistant to standard filtration and even advanced filtration methods like reverse osmosis. But UV AOP has sort of found is sort of a technology that can treat this particular contaminant. In addition, we have surface water remediation. A good example would be drinking water plants drawing from lakes and rivers that have seasonal issues with algal bloom. So if you hear things like algal toxins, microcystin, taste and odor causing compounds, this is a good example of what UV AOP can be used for in a surface water application. Another one would be potable reuse. And when I say that, I mean advanced treatment of wastewater to such a high standard that that effluent can be reused pretty much immediately for drinking water applications. Commonly used in drought-prone areas, California, Texas, and others. And in order to provide long-term water sustainability, a UV AOP is often used for contaminant treatment in those applications as well, amongst others. So what are some of the common factors that influence UV AOP performance? I'm going to go through a little bit of what do we need to look for, what considerations do we need to take into account when designing an effective UV AOP system. And there are three here that I would like to cover. First is UV transmittance. This is basically a measure of how well UV light can transmit itself through the water. Obviously, if it can go further into the water, if you have very clean water, this is better because the UV light can generate more radicals, leading to a much more efficient UV AOP system. The other two here kind of come back to the water matrix of the water. So we have nitrate, which is naturally found in water. And what this does, when it's present, it can absorb certain wavelengths of UV light, particularly low wavelengths in the minus 200 in the 240 nanometer range. And what that does is it takes that UV light out of the water, making it unavailable. So this is a bit of a deterrent for the UV AOP system. It can also become nitrite in the presence of low wavelength UV light, and nitrate acts as a scavenger. And scavengers is basically a blanket term we use to describe organics and inorganics that compete for hydroxyl radicals. And the more competition, the less these radicals are available to treat the contaminants we want to treat, again, resulting in a much less efficient system. So the important thing to remember here, though, is that every water has different characteristics and challenges. These factors are different in different waters, even in a small geographic area. So it's important to understand the type of water that we want to treat and what is in that water before proceeding to a full-scale sort of design. So what are some of the advantages of UV AOP over other treatment technologies that can be used to treat chemical contaminants? Well, first of all, UV AOP, as well as other oxidation-based technologies, work directly at the molecule level. Activated carbon, reverse osmosis, air stripping, they don't destroy contaminants. They just take the contaminant out of the water and put it somewhere else. UV AOP destroys contaminants, actually taking it out of the environment. And one major advantage of UV AOP over other oxidation technologies, let's say ozone, is how fast it works. Hydroxyl radicals are one of the most powerful oxidizing agents that is commercially used for this purpose. So treatment is happening instantaneously within a UV chamber. There's no need for extended contact time, contact basins, diffusing basins, or anything like that. This provides a very small footprint for contaminant treatment over other oxidation type technologies. In addition, the hydroxyl radical oxidation pathway has not shown bromate formation when bromide is present in the water. The use of ozone has been shown to generate bromate, which is a regulated byproduct of treatment, and this is a much lower concern when using hydroxyl radicals for contaminant treatment. In addition, since we are using UV chambers to generate these radicals and treat chemical contaminants, we can also simultaneously deliver chemical-free UV disinfection for bacteria, protozoa, or viruses. So if you have issues with contamination, but also are required to obtain a level of disinfection for whatever water you're treating, be it drinking water, wastewater, or industrial, UV can provide dual disinfection at the same time as UV oxidation. So this, a good example is when this would be used would be, let's say, you have seasonal issues with contamination, such as algal blooms, and you only need UV AOP for maybe 1 or 2 months of the year. But if you're a drinking water plant and you require either virus credit or cryptosporidium credits, you can use UV for the rest of the year to achieve those credits as well. So you're getting more out of your complete system. Some of the inherent disadvantages of UV AOP, I'll cover a couple of these as well. First is that when you're using hydrogen peroxide, not all of it is converted into these hydroxyl radicals. Some of it remains after the UV system as a residual, and typically this residual needs to be removed from the water before it enters a distribution system of some kind. This is a process we call quenching. There are a couple of ways that this quenching can happen. Both with advantages and disadvantages. Chlorine can be used to quench residual hydrogen peroxide. Great, because you can keep chlorine in the water to act as a secondary disinfectant if you need it. Not so great if you are concerned about trihalomethanes or those sorts of chemical-based disinfection byproducts. Activated carbon is another useful tool for quenching residual hydrogen peroxide. No concerns about byproducts there, but typically comes at a higher price tag than using chlorine. An additional benefit of using activated carbon is that it can also be used to treat chemical contaminants that UV AOP cannot treat. Namely, a good example would be the PFAS contaminant, which I'm sure many of us have heard about. So there are ways where you can come up with a holistic UV AOP system that can treat contaminants that are, let's say, resistant to filtration, like 1,4-dioxane I mentioned previously, but also treat contaminants that are resistant to oxidation, such as PFAS. Quite often in a groundwater contaminant treatment situation, there often isn't just one contaminant that needs to be treated. There's usually a whole bunch of them that need to be taken out of the water. So it's important to come up with a holistic system that can try to treat everything. Another thing with UV AOP, as I mentioned before, UV transmittance is very critical to the efficiency of UV AOP. So high quality water that is quite clear, hopefully filtered, is certainly the best water to use. If you have high turbidities and solids or colors in your water, UV AOP might not be as economically advantageous. So that basically my speaking points on technology. I hope there's some good questions. I'll just review do's and don'ts associated with the technology. First of all, do make sure you know your water. Manufacturers, we do have lab services and piloting services to run water samples and kind of figure out what the characteristics of your water are to design an effective UV AOP system. Do not think that one design just works for everybody. Everyone's water is different. We need to be finding that balance between oxidation and UV, and it really just takes some very basic water analysis to come up with the best design. And lastly, do trust experience. Trojan Technologies, we have almost 1 billion gallons of water installed, treated per day to manage these kinds of systems. Do make sure if this is a technology you're not familiar with and you want to learn more about, make sure you trust experience when it comes to this. And with that, that again concludes my speaking point. So thank you for your attention. If you want to get a hold of me and learn more after this discussion, my contact information, I believe, is provided on the slides. Thanks again.
Excellent. Thank you, Scott. If you can see my screen, I'm going over and switching it right now. We're going to open it up to questions and answers. And I know that Q&A normally we can have a long list or we can have a short list, but I have a couple questions myself. So if anybody has any, you can kind of punch them into the box right there, into the chat box. We already have a couple that are coming through. Or don't be shy. You can go ahead and turn on your camera, or at least pick up some of the questions. So the first one we have here is coming in from Diana out of California, and it has, so the use of UV AOP typically require higher alloys for materials of construction. Or is electropolished passive 316 steel good enough? Guessing this is based on the chamber that we're using.
I would say that typical 316 stainless steel is good enough. We use that in most of our products. Sometimes we have used other steels for corrosion resistance, but I don't see a reason why 316 steel wouldn't be good enough. It certainly wouldn't have an influence on the UV AOP performance.
So you'd be using the same standard reaction chamber that you would use for any other UV process.
Absolutely. Oh, with the notable exception is we would probably want a more powerful UV system for UV AOP because the UV doses that are delivered for AOP applications are traditionally much higher than, let's say, standard disinfection for drinking water or wastewater.
Right. Okay. So speaking of UV, and because we're comparing it to UV, I had a question, and I'm surprised we didn't quite cover it, but of course we were trying to keep it as short and compact as possible. What spectrum light are we running? Are we operating at a standard 254 nanometer dose, or spectrum, or are we using the 185, 186? What are we running this on?
That's an excellent question. For most applications, we are using the 254 low pressure lamp emission spectrum, basically at 254. Medium pressure, that would be for low pressure lamps. Medium pressure lamps, which have a polychromatic spectrum that emit at various wavelengths, can also be used. But I mentioned that nitrate absorbs water at below 240, and medium pressure lamps can emit at 240. So nitrate has a much more of an impact on medium pressure UV as opposed to low pressure UV. Now, you mentioned the 185. I believe that is known in some circles as vacuum UV. And there is research being done to see whether or not that particular wavelength can on its own produce radicals without the influence of a oxidant like H2O2. To my knowledge, that is not very commercially limited. It's a very inefficient process, and it is not being used on a huge commercial scale. But for the applications I'm talking about here, we're talking almost exclusively in the 254.
Okay, so then that kind of leads me over to dose. What, your standard UV disinfection is operating at 40 millijoules per centimeter square. Right. Is there a specific range, and how would that change based on water quality?
Yeah, that's a good point, and it's a very important thing to bring up. In terms of a range, it's very hard to say. If I were to throw out a couple of numbers, I'd say between maybe 800 and 1200 millijoules. If we're looking for a measure, if we're looking for a measure of scale here, but this depends again on those criteria that I mentioned before, UVT and scavenging demand. We can, let's say, increase hydrogen peroxide delivery and at the same time really reduce the UV dose. So you can, let's say, have a UV AOP system that delivers a 600 dose at 15 parts per million peroxide, or a UV AOP system that delivers 1,000 dose at 10 ppm peroxide, and they would do the exact same treatment. It really comes down to, well, how much do you pay for power? How much do you pay for hydrogen peroxide? These systems can be very customized for a customer's particular needs, and to find that right balance to make sure not only do you get the treatment, but you get that treatment at economic operating costs as well.
So some contaminants, of course, we know are seasonal, like if you're going into algae blooms or cyanobacteria or even 1,4-dioxane. And you mentioned that we're operating this sometimes, this would be operated at 800 millijoules per centimeter square, which is very high. Is there a way to, I guess, change that dose based on what your season or what you're targeting?
Yes, absolutely. Most control philosophies with these systems allow for just that. So a good example, like if this UV system behind me, you might be able to see that there's about 4 or so banks of lamps that are installed in here. For a UV AOP application, we might use all 4 of those, turn all of those lamps on for UV AOP to deliver, as you say, like 800 dose or whatever it has to be. But during times of the year you don't need UV AOP, these lamps, these banks can be turned off, and you can operate with maybe only one section of lamps turned on to give you the lower dose needed for disinfection. This would save on energy costs and lamp costs as well. So many UV AOP systems are designed with that in mind.
Okay, and then I've got the last question here. It says, are there smaller scale applications for UV H2O2 for other AOPs? I'm guessing something more on the residential or light commercial.
That is something we're looking at in order to be able to get effective. The key is in order to be able to get effective mixing. Those solutions are definitely available. The main concern is making sure that your flow through your chamber is high enough so that you don't hurt the lamps. We can treat down to, let's say, 100 gallons per minute and things like that as well. So definitely, I'd say in the light commercial, this application is certainly possible. Once we get down to like under the counter type residential applications, it becomes a little bit more difficult.
Yeah. Okay. So the last question I have, just to wrap up, you mentioned, without going into residential or light commercial or something like under the sink, and we are operating at your standard 40 millijoules per centimeter square, and it's all dictated by dose. So dose additivity means that you can operate a 200 system and then crank it down to, say, 20 gallons per minute, and then you're achieving a much higher dose than, your standard 40 millijoules. So could you turn, I guess here comes the question, can you turn a standard UV system, like something that's running at whether it's 100 or 150 gallons a minute, crank down the flow, so restrict your flow, add in whatever chemical you're doing, and turn it into something that can run UV AOP? So say 100 gallons a minute to 5 gallons a minute. Would that work?
That makes perfectly logical sense. It really is just injecting hydrogen peroxide into a UV system. There's nothing special about the UV system that makes it, it magically works for UV AOP. So yeah, you can definitely do that. As a person experienced in this technology, I wouldn't say do that without talking to somebody first. Mechanical concerns might be, are you dropping your flow to such a low level that you can't cool the UV lamps effectively? That would be a mechanical concern. But from a practical concern, I don't see a reason why you wouldn't be able to do that now.
Excellent. Well, thank you. I don't think we have any more questions here or so much for time. I do want to add something here to the very end. Somebody just sent me this this morning, and I know that it's one of those things that just breaks my heart when I see something like this, so I thought I had to share it. And without going into any kind of personal rant, I know that we've made a big deal about straws, and yes, save the turtles. And, we went on an all-out war for straws. And then when I take a look at this, I'm like, well, why didn't we do something like this about just plastic pollution overall? So I just wanted to share that. That's just a quick little thing. I don't mean this to be a downer for the day, but it does. As soon as I saw this, it really broke my heart. I'm not really sure where this is, but it did really surprise me. With that, and wrapping up, I do want to make sure that everybody sees in the next 2 weeks, we're going to have another webinar. We're going to be looking at PRV, or pressure recovery valves. Unfortunately, this has been delayed. We've had some scheduling conflicts, so thank you, Scott, for being able to cover this. I want to thank you again for your help with this. This has been great, a lot of good information. If anybody has missed any of the webinars, we do have our YouTube channel. You can go in there and have a review. I'm going to share the link here shortly so you can all have a copy. So with that, thank you very much, everybody. Thank you for coming, and I will see you again in 2 weeks. Goodbye.
Thank you, everybody.